to today's explainer. Let me ask you a question right up front. Is making a microchip really just like assembling a standard PC or a smartphone? You just grab some parts, slap them on a board, and solder them together, right? Well, today we're going to completely shatter that illusion. We're stripping away the mysteries of semiconductor manufacturing to show you exactly how raw physics and chemistry are transformed into the brains of our modern world. Okay, let's dive right into this. Here is our roadmap for today. 1. Not just electronics. 2. Building the silicon high-rise. 3. The 5 core modules. 4. Lithography and etching dance. 5. The EMIUS software challenge. And 6. Why Fab IT costs millions. Section 1. Not just electronics. We really need to reset our foundational understanding of what industry we're actually looking at here. So I posed this provocative question to you at the start. Is semiconductor manufacturing just building electronics? When you think of an electronics factory, you probably picture robotic arms clamping down green circuit boards and rapidly snapping components into place. But if you walk into the front end of a semiconductor fab, you're not going to see any of that. Think about the contrast here. Standard electronics manufacturing absolutely relies on a bill of materials, or a BOM. You need resistors, capacitors, and physical clamping tools, jigs, to hold the whole thing together. But the semiconductor front end, it's entirely different. It starts with a raw silicon wafer, and honestly, it ends with that exact same wafer. There's no traditional BOM, there are no clamps holding pieces together. Instead, it's this incredibly complex, discrete process completely governed by physics, chemistry, and optics. And here's the real kicker. During this entire front-end manufacturing process, there are absolutely no electrical properties, none. It's simply raw material manipulation until the very end. So, if we aren't snapping electronic pieces together, what exactly are we doing? This brings us to Section 2, building the silicon high-rise. The absolute best way to visualize a microchip isn't as a flat puzzle, but as a towering skyscraper. Because we want to pack as much computing power as humanly possible into the tiniest volume, we have to build vertically. We construct this silicon high-rise layer by layer. First, we lay down a pattern of what will eventually become an electrical circuit. And then, we seal it with an insulating protective film, like an oxide layer. Then, we build the next floor of circuits right on top of that, insulating it again. We just stack and stack. But remember, as we're pouring the microscopic concrete and steel of this building, there's no electricity running through it yet. We're just physically structuring the layers. Now, how do we physically build these microscopic floors? Let's move to Section 3, the 5 core modules. A modern wafer fab might easily have hundreds or even 1,000 incredibly expensive machines, but practically all of them fall into one of these 5 core processing modules. First, thin film deposition, which lays down those foundational layers. Second, diffusion and ion implantation, which alters the silicon's properties. Third, etching, which carves out the actual structures. Fourth, CMP, which polishes the wafer flat. And fifth, lithography, which is the crucial optical step. Now, what's really fascinating here is the sheer extreme of the physical environments we're dealing with. When we deposit protective layers in the thin film module, we actually consider 600 to 800 degrees Celsius to be a low-temperature process. Compare that to the diffusion module. Here, wafers are placed into towering furnace tubes to alter their impurities and create oxide layers, operating at searing temperatures well over 1,000 degrees Celsius. The physical stress these raw wafers endure is just staggering. Let's see how this builds into the most critical partnership in the entire factory, in Section 4, lithography and etching dance. If thin film and diffusion give us the raw concrete floors of our high-rise, lithography and etching carve out the rooms and hallways. It is a highly precise 4-step physical dance. First, the wafer is coated with a light-sensitive chemical called photoresist. Second, it's exposed to intense ultraviolet light through a patterned mask. Third, we develop it, so the light either hardens the pattern or makes it soluble, depending on the specific process. And finally, in step 4, the wafer is sent to etching, where chemical solvents or physical plasma literally eat away those exposed underlying layers, leaving behind the precise circuit structure we want. The absolute star of this dance is the stepper, typically made by companies like ASML. This machine is a literal optical marvel. It projects the circuit pattern onto a single section of the wafer, called a die, and then literally steps over to the next section to repeat the process. Because the precision here is measured in nanometers, these massive machines actually float on magnetic levitation grids to eliminate even atomic-level vibrations. And crucially, all of this has to happen in specialized yellow-lit rooms because normal white light contains UV rays that would instantly ruin the highly sensitive photoresist. But here's the catch. The stepper can't do its job if the surface isn't absolutely perfect. That's why chemical mechanical polishing, or CMP, is mandatory. As we build our high-rise layer by layer, the surface naturally gets a bit uneven. If you shine the stepper's perfectly focused light onto an uneven surface, the light scatters and the pattern is completely ruined. So CMP grinds the wafer back down to absolute microscopic flatness before the next layer can be drawn. So, we've established the intense physical reality of the fab. Let's pivot to Section 5, the MES Software Challenge. Why exactly does standard manufacturing software fail spectacularly here? Well, it comes down to concepts like the multi-chamber machine. In a standard factory, a machine is just a machine. Product goes in, product comes out. Simple. But in a semiconductor fab, a single machine might have 2, 3, or even 4 completely separate reaction chambers attached to it. Wafers entering the exact same machine might take entirely different internal routes. Physically, it's one giant piece of equipment, but logically and functionally, it acts like multiple independent machines simultaneously. And this setup illustrates exactly why this is an absolute IT nightmare for traceability. Let's say a machine has 2 chambers. Chamber A is perfectly tuned and produces 100% good wafers. Chamber B has a hidden defect and destroys every single wafer it touches, yielding 0%. If your standard factory software just tracks the machine as a whole, it's going to tell you the machine has a 50% yield. That is totally useless in a fab. The IT system, the Manufacturing Execution System, or MES, must be custom-built to trace the exact chamber every single wafer passed through to isolate the exact source of a defect. The business logic required just to get an IT system through the front doors of a fab is incredibly strict. Just look at these unique requirements. First, you need form batching. The software has to know how to perfectly group 4 to 6 different lots of the exact same product and process to efficiently fill up one of those massive high-temperature furnace tubes. Then you need machine QC, the ability to run quality checks on the machine's status itself, totally independent of the actual product. And you have to expertly manage seasoning, the really complex warm-up periods a machine requires before it reaches the precise physical conditions needed to process a live wafer safely. Furthermore, the software actually has to track wafers that don't even end up in a computer. These are called non-product wafers, or NPWs. For example, if a furnace tube isn't completely full, the airflow becomes unstable and ruins the whole batch. So the system must automatically deploy dummy wafers to fill the empty gaps and stabilize the air. It also has to deploy monitor wafers at the top, middle, and bottom of the tube just to measure the process accuracy. The IT system has to track the entire life cycle of these dummy wafers, how many times they've been used, when they need chemical cleaning, and when they must finally be scrapped, even though they will literally never be sold to a customer. This brings us to our final section, Section 6, Why Fab IT Costs Millions. Let's tie all these intense physical and software demands directly to the bottom line. Why do semiconductor companies routinely spend tens, sometimes hundreds of millions of dollars on highly customized IT architecture? Because of this central number you see right here, 0. The cost of a single advanced stepper machine is easily over $100 million. The value of a single batch of advanced wafers can be astronomical. Because the equipment and the materials are so incredibly expensive, the system's tolerance for making a routing or processing mistake is practically 0. So the crucial point is this. You literally cannot run a modern fab with people walking around with clipboards. It requires complete unmanned automation and paperless tracking. The control logic for simply moving a lot in and out of a multi-chamber machine is mind-bendingly complex. The traceability must be flawless, covering both the final products and those dummy wafers we talked about. The system stability must be absolute. Standard manufacturing software simply collapses under these specific, intense physical requirements. Which brings us right back to our core theme, perfectly captured in this quote. Semiconductor front end is not electronic manufacturing, but the final electrical result produced by a process of chemistry, physics, and optics. We aren't building circuits with solder and wire, we're literally sculpting them with ultraviolet light, chemical solvents, and 1,000-degree furnaces. And I want to leave you with this final thought to ponder. If managing this interplay of light and chemistry already requires hundreds of millions of dollars in zero-tolerance, highly customized software today, how exponentially more complex will these IT systems need to become as we push semiconductor manufacturing down to the scale of individual atoms? It's a truly fascinating engineering puzzle, and we'll certainly explore it more in our future explainers. Thanks so much for joining me today, and keep learning.